So this video gives you an introduction to summation notation, and it leads into Riemann sums. The sum of n terms, a sub 1, a sub 2, up to a sub n, written in sigma notation is as you see. The left-hand side of this is spoken as the summation as I goes from 1 to n of a sub I equals the actual summation. I, in this case, is called the index of summation. A sub I is the ith term of this sum, and a sub I is understood to be some kind of function of I, and the upper and lower bounds are n and 1. Now the index of summation is considered a dummy variable. It's not actually present in the sum, so for that reason you can call it anything. So if you were to replace the I with a k or with a j, you would still get the exact same summation you see on the right hand side. To go through a few examples, let's evaluate these summations to find out what their sums would be. Now by definition, this would then be evaluate this function for the I values of 0, 1, 2, up to 5, and then just add up the evaluations. That will give you 3 plus 4 plus 5 plus 6 plus 7 plus 8, and then you would just add those numbers together in order to get the answer. Let's now evaluate this second summation. Again, just evaluate the summation as k goes from 3 to 6. So it's 3, 4, 5, and 6. In each case, once you do the evaluation, just add them all together. So if you evaluate when k is 3, you would get 3, and then the next would be 5, and the next would be 7, and the next would be 9. So that's when k is 3, 4, 5, and 6. And then this sum, when you add it up, that's the answer. That's what this symbol means. So for now on, we'll say that two summations are considered equivalent if they generate the same terms in the same order in the addition. These three summation notations actually refer to the exact same sum. In each case, each sum is 0 plus 2 plus 4 plus 6 plus 8. Now, they'll be considered equal if they represent the same value. So it's possible that two summations could add up to the same sum. But just because things add to the same sum does not mean they were equivalent summations. So for example, 1 plus 3 is 4. So the sum is 4. But that's not the same summation as 2 plus 2, even though 2 plus 2 is still 4. They are not equivalent summations. They are the same sum. You should notice in the three examples I gave you that these were all equivalent summations and therefore the exact same sum because they're adding up the same numbers. But to represent that summation, you can use a different generator. That's the function being used. You can use a different index variable. Sometimes I use k, sometimes I use I. And the upper and lower values, the upper and lower bounds did not need to be the same. Sometimes I had 0 and 4. Other times I had 1 and 5. So it's completely possible that for one sum, there are many, many, many ways to represent that summation. But they are all equivalent as they all give the same summation. And therefore, of course, they give you the same sum. Now that we've introduced a definition, it might be nice if there's any kind of algebraic properties that this summation notation possesses that we know about them. Now, the first obvious one is that if you have a summation of a constant multiple, that's actually a constant multiple of a summation. This is just the distribution property written in summation notation. If you have a constant times a quantity in parentheses, you can distribute the constant multiplication to every single term in that summation. So that's why that property would be true. And then if you have a summation of a sum or a difference, it's a sum or difference of summations. This is using two properties at once. It's using associativity and commutativity. You're essentially saying if you want to add up a whole bunch of terms, you could add up all the A's first and then all the B's next. Now there are some special cases. If you add up a constant as I goes from 1 to n, that means you evaluate the function c when I is 1, when I is 2, when I is 3. But in each case, when you evaluate that constant function, you get the constant c. So that summation is really adding c in a summation a total of n times. So of course the sum is n times c. If you take the summation of 1 plus 2 plus 3 up to n, that summation notation is what I have here on the left, and its value in the end would just be n times n plus 1 over 2. That allows us to quickly find the summation of a bunch of integers starting at 1 and increasing up to some final value n by just evaluating n times n plus 1 over 2. You also have similar formulas for the sum of the first n squares and the sum of the first n cubes. You'll notice that in a lot of the problems I'm about to give you now, that we'll use these formulas in order to find the value of a sum without actually using the definition. For example, you would never want to add up the first 1,000 integers from 1 to 1,000 by hand. You would instead use one of these formulas. As an example, let's find the summation as I goes from 1 to 10 of 3i squared minus I plus 2. Now we could do it the old way. Evaluate when I is 1, evaluate when I is 2, evaluate when I is 3, up to evaluate when I is 10, and then add those values together. But that seems painful. So instead, let's use the properties I just gave you. The summation of a sum is a sum of summations. And a summation of a constant multiple is a constant multiple of a summation. That allows me to distribute this symbol through all the constants, all the additions and subtractions, and just take the summations of the resulting functions. But we have a formula for the summation as I goes from 1 to 10 of I squared. So we have this one right here. And I have a formula for the sum as I goes from 1 to 10 of I. So I have a formula for that one too. And this is the summation of a constant. I have a formula for that also. I'll just replace each with what they equal to by the formula I have. In each case, it's going from 1 to 10, and the formulas go from 1 to n, so I just use n is 10 for each of those formulas. And that gives you these. All I did was evaluate each one when n was 10, using the correct formula as I went. So the answer is, the original summation is just 1,120. Now, if you want to check that on your calculator, you can. Your TI-83 or 84, you can go to second stat to go to your operations to generate a sequence. You put in your generator the function being used in the summation and express it as a function of x usually, and then comma, and then you write down the variable being used in that function, which in this case is x, and you write down how many terms you want. So we'll go from 1 to 10. That generates a set of the terms, the first, the second, and third. So the first term in the summation is 4, the next term in the summation is 12, and so on. If I then just take the sum of that answer, it adds them all up. And look, we got the right answer. This way, if you want to, you can do it on your calculator, or if you wish, you can do it using algebra. The algebra, though, is what we'll be forced to use later on when we have only symbols. So let's go back to an example we had in our previous video. Remember, I was trying to approximate the area underneath the function f of x equals x plus 4 over 4 over the interval from 0 to 4. That gave us a trapezoid. So we know how to find the area of the trapezoid. I'm just interested in approximating that area. So keeping in mind with what we've done so far, I would break the interval from 0 to 4 into subintervals. In every subinterval, I would then pick an x value. This would determine, by evaluating the function at that x value, the height for the rectangle over that portion of the interval above that subinterval. I would then find the area of that rectangle and add up all the areas of the rectangles. I just want to give you an idea of kind of what it looks like. Suppose we go with a regular look. That means all the subintervals would be equal length. And I'll pick the right endpoint in every single subinterval. That would generate these rectangles. I would then find the area of those red rectangles, and that would be an approximation then to the area in blue. It's clearly an overestimate. But realize we have some freedom here. When I go about choosing the subintervals and when I go about choosing the x values, there's a lot of freedom in the process. Let's just keep the actual subintervals here, and let's just change the x values that I pick in each one. Here what I did was I just went and picked kind of random x values in each subinterval, and I found the corresponding heights and built my rectangles. Notice that sometimes the rectangles are slightly underestimates, other times they're overestimates. I would bet, though, that this winds up being a better approximation than the previous one. But even though it's a better approximation, notice, though, that it didn't change much. Changing the x values in the subintervals did not change the overall sum of all the areas of all these rectangles very much at all. Now, we can go further. This time, let's say I'll just make my subintervals in a way where they don't have to be equal lengths. And again, just randomly pick x values. I could get that. That doesn't look like a terribly good approximation. But the reason is because the rectangles are so wide. So what if I do it again, but this time use a lot more rectangles so that overall all the rectangles get thinner? In this case then, it doesn't seem to matter too much how I go about picking my x values in each of these subintervals. The overall height of the rectangles that I create can't vary that much. So the sum of the areas of these rectangles should all be kind of close to each other, no matter how I pick the actual choices in every subinterval. And it doesn't really seem to matter how I choose to break up the subintervals. And it doesn't seem to matter how I built. And it doesn't seem to matter how I break the interval from 0 to 4 into subintervals. To generalize this process, let's suppose that f is defined on a closed interval from a to b. Separate the interval from a to b into subintervals via partition, which is just a sequence of numbers x sub 0 up to x sub n that begins at a, ends at b, and is always increasing. The subintervals then are defined by the beginning and end of two consecutive x values in this list. If c sub I is any number in the ith subinterval, where the change of x sub I is its length, then the summation of a bunch of products, where the products are the function evaluated at this choice value times the length of the subinterval, we call that a Riemann sum of f using the partition P. Notice there's many such Riemann sums, even for one given partition, because you can always, with a fixed partition, you can still change the x values that you choose in every subinterval however you wish. So you can get many, many, many different Riemann sums because we can make our choices different and we can use different partitions and therefore get different subintervals. It is useful to see a visual depiction of what a Riemann sum does. So instead of being constricted to only using positive functions, notice the Riemann sum never says that. The function is just something defined on the interval from a to b. But still, you can, over that interval, breaking it into subintervals, for each subinterval you can make a rectangle. The only difference now is sometimes the function is positive and sometimes the function is negative. The product, though, of the function at ci times the change of xi, that could be either positive or negative or even 0, depending upon the function value. So when you add up all these products, think of it like you're adding up positive areas to some negative areas and sometimes 0 areas. This is good, by the way. This is actually a good idea because there's plenty of times when we want to compute something and we're looking for a net result. So there's positive and negative values and we want to add them up. So this is actually okay. Now, with so many different choices at our disposal when making a Riemann sum, it'd be nice to have a go-to Riemann sum. So this is essentially it. We choose to use n equal length subintervals when we make our partition. So that means then that the length of every subinterval is found by taking the length of all the subintervals, b minus a, and dividing by n. That also means then that the length of a subinterval no longer depends upon which subinterval you're in. So we don't tend to use then subscripts. We don't write change of x sub k. We just write change of x. And in the kth subinterval, we're just always going to choose the right endpoint, as it just makes, again, our life easier. But then, that means that the kth such x value can be found by starting at the leftmost of the interval, that's x sub 0, and then adding the lengths of the subintervals until you get to the kth such subinterval. By adding up all those lengths, you travel along the real line from x sub 0 up to the right endpoint of the kth subinterval. But the length of all these subintervals are the same number. They're all b minus a, and there's k of them. Also, the very first x value in this particular partition is the leftmost x value in the interval from a to b. So x naught is 0. That then gives you a formula that if you want to know what the choice point is in the kth subinterval, it's always a plus k times b minus a over n. Using these choices, the normal Riemann sums formula becomes just this one. And notice then the summation on the right-hand side now is a function of n only, because the k is a dummy variable. When you evaluate that expression for different k values, there are no k's. But the n, though, is a variable that does not vanish in the end. So the summation, when you're finished, will be a function of n only. And in the case of area, that should give you the net area between the curve and the x-axis for that many rectangles using a regular partition and always picking the right endpoint for every subinterval. This does not need to be an upper or a lower sum. It need not be an upper estimate or a lower estimate because I don't know what the function is. If the function is always increasing, then this will correspond to an upper estimate. If the function is always decreasing, then this will correspond to a lower estimate. Those will be called then an upper and a lower sum. So just to connect what we did in the last video with what I just mentioned, let's do the problem we did before. We have the function was x plus 4 over the interval from 0 to 4. Let's just begin by subdividing that into n equal subinterval lengths, where the length would then be 4 divided by n, b minus a over n. That would then give us n different subintervals, where it would be 0, then 4 over n, then 8 over n, then 12 over n, and so on, until you get to 4. In every single subinterval, we'll just pick the right endpoint. But the formula for doing so would then just be k times the change of x, plus a. A is 0 here. So that's 0 plus k times 4 over n. So that's 4k over n. Using our normal sum, the sum of those areas of those rectangles would be their widths times their heights. So it's the function times an x value times the width, plus a function evaluated at an x value times its width. But here, the change of x in all cases is just 4 over n, and we have a formula for the choice point that we're picking, as we're always picking the right endpoint. So that would then be 4 over n, 8 over n, and so on. That summation then represents the sum of the areas of these n rectangles for our particular function. But we can condense that into simple summation notation. This is exactly the formula I gave you on the previous slide. It was the function evaluated at a plus k times b minus a over n. That function evaluation multiplied to b minus a over n. And then you would just take those products and sum them up as k goes from 1 to n. So let's evaluate that sum. Well, we know what the function was. It was x plus 4 over 4, so I just evaluate that when x is 4k over n. That expression, I want you to go and multiply the 4's and the division of 4, let them cancel to give me a simpler fraction, 4k over n plus 4 over n, the summation as k goes from 1 to n. And then I want you to think of that summation as a polynomial in k, because in the summation, n is fixed, it's a constant. So 4 over n squared, that's a constant, times the variable k, plus a constant 4 over n. Next, go ahead and distribute the summation through like you always would. You'd have a summation being distributed through a constant multiplication of 4 over n squared, so that would come out. You would then have the summation of the k, plus. Then the summation would be applied to the constant, 4 over n. We don't take that constant out. We'll just leave it there. Thing is, though, is I have formulas then for this one and for that one. The first one's the sum of 1 plus 2 plus 3 plus 4 up to n. That's the sum of the first n integers. The second summation is the sum of a constant as k goes from 1 to n. And we have a formula for that one too. Just using those formulas. That would then give you this particular expression. Notice the k is gone, as it should be, because in a summation, the index is just a dummy variable. You won't see it in the n answer. I'll just simplify that, and that gives me this 6 plus 2 over n. That would then give me the area of these n rectangles added together. So I'll just go ahead and use different n values when n is 1, 2, 4, and 6. These gives me the estimates. And these are the exact same estimates I got before. In the previous video, I only did when n was 2, and we got 7. And I only did when n is 6, and that was the 6.3 repeating. But these Riemann sums, as a function of n, each of them are approximation to the area that we're trying to find. And it appears that if you take the limit of these Riemann sums as n goes to infinity, that the limit exists in 6. Now when you think about this limit, remember that the change of x, that was b minus a over n. So if n goes to infinity, the change of x goes to 0. That means I have lots and lots of subintervals. That's the n growing without bound. But every single rectangle becomes insanely thin, which means we should expect that each rectangle approximates its portion of the area better and better and better. So we'll then define, we'll say that the area that we're after is the limit of those Riemann sums, and the area is 6. Now, as just for fun, as I said, this region that we're trying to find the area of, it's just a trapezoid. So we can find the area of the trapezoid. It would be the sum of the bases, which here is 1 plus 2, that's 3. And then you divide it by 2, that'd be 3 halves. And then you multiply it by the width of the bases, which is 4. If you take 3 halves times 4, you get 6. So notice that our particular technique, even though it's a limit of an estimation, we actually get the exact answer in that limit. And that gives you a basic introduction to summation notation and Riemann sums. What we'll do next is we'll explore what happens if we don't use a regular partition, a partition where all the subintervals are the same length. And what if we don't use the right endpoint? Should we get, in the end, in a limit process, will we always get the limit of the Riemann sum as one number only? And if we do, what would that mean? And finally, is there a better way to compute this thing? Because no one wants to do it by hand like this. There's got to be something faster.